Hello, everyone. Welcome to the Data Science Mentor Program. It's a mentor program dedicated to folks who are learning data science from scratch using mentorship as a service. How are we all doing? My name is Pablo. I am a data science professional, a data science educator, program manager, and I build communities around data science, machine learning. And as we proceed, we grow into the different moving parts of data science and machine learning. And this cohort today, we're going to be talking about polynomial basis function. Sorry, I have to make it's called polynomial basis function. Now, the polynomial basis function is a clever trick, and it's important we talk about that. And it's a clever trick introduced to linear models. Linear models need this really well, and so we're going to look at what it's about, and we're going to understand why it has become an interesting tweak in linear models. So we'll start off by explaining some of the things, and I like this part where I mentioned it's a clever trick. So the polynomial basis function is a clever trick. Now, yeah, so the polynomial basis function is a clever trick. Now, why is it a clever trick? And it's what explaining. When you build a linear model, you're trying to find a relationship. You're trying to draw a straight line between an observed feature and a predicted feature. Now, before you predict on data that isn't seen, you'll typically use data that you have. They're called training examples. But at the same time, you break the data into bits. There's a bit for training and there's a bit for prediction, and that bit for prediction is the one is where we play pretend like we haven't seen this data in the past. Now, because it's a linear regression, a linear model, we're trying to find linear relationships between an input, which is basically a feature, and the output, which is what we're trying to predict. And if you think about the first principles for linear relationships, they're saying, look, if it's a positive relationship, if it's a positive relationship, then one feature on one hand goes up and the output goes up at the same time. It's like, you know, it's like saying the more you eat, you put on weight, sort of, and not for every body type in the world, but you get the drift. But now the interesting thing is it's not all relationships that are linear. There are some features that act out in a non-linear fashion. And how do you deal with situations like this when you are building a linear model, but some of your features have non-linear status? So that is what we're trying to do. Now, the interesting thing about building linear models is trying to draw a straight line. So that's why they say the line, you hear stuff say the line that best fits, which is observed features, predicted features. So, but how do you deal with a situation that is interesting? Now, here, and I mentioned in the last session that there are situations that call for this, and so that's what we're going to talk about. So, when you use polynomial basis functions, you're basically transforming your inputs. So this is the trick. You have an input. So we have an input x, And when we say an input, this is a feature. So if we're talking about trying to predict house price, the size of the house is an input, right? And so, but what now happens if I mean, it's easy to think that the larger the house, the bigger the price, which seems like a perfect positive linear relationship, right? But what if it is not, and it's important? And I know you're thinking, so how do we achieve this? Now, to do this, we have an input X, and we transform the input so the model can learn their discrepancies. So we transform the input so the model can learn like, let me call it discrepancies, that there are differences, right? Yeah, so the model can learn their discrepancies. So think about it like real life. So what we have going here is the polynomial basis function will take an input, say, so what it does is take an input X and transform the input to versions like, say, x raised to power 2 or x raised to power 3, right? Then try to fit it into a new space, and in this space it starts to act like a curve. This new space now tries to be like a curve that can find the different discrepancies that exist between relationships in features and targets. Now, one way to look at this is to think about stuff. Now, let's look at a situation. Say we're looking at the speed of a car versus fuel efficiency. And let's say you're trying to model how fuel efficiency changes with speed. So if we have a situation, say, so in essence, like car speed, this is a situation. So we'll call this a situation, right? So we're looking at car speed versus fuel efficiency. Now, fuel efficiency is a huge thing, especially for car users. There's always this conversation about, oh, you have to buy a Toyota is fuel efficient and all. Now, so let's assume, right? We'll have this assumption. So let me take this out of here. Let me put this first part here. So let us talk about, like, call this a real world use case. A real world use case. Now, so that's why this is the situation. Now, let's say, right, that we notice. So let's say we notice. Let's say we notice that at low speeds, right, miles per gallon increases. So let's say we notice that at low speed, right, MPG, or we might say kilometer per gallon, right? But we can say miles per gallon, which is a very popular way to look at it. Miles per gallon increases. So let's say that's it. And at high speed, let me put it here. And at high speed, we also notice that MPG decreases. Now, this isn't sort of like a straight relationship, and The reason why I say this is because it looks like it's like a linear relationship, but it's sort of like you have to understand that the car does not drive the way you would think. I'm going to be driving higher and then more fuel is taken, or I'm going to be slowing down. We drive the car. You drive the way you drive the car. It's not linear. Basically, at one point you can be driving your car in a way that maybe you're thinking about life, you're asking yourself existential questions, or for some reason you're excited and you drive at a speed and you stop, or whatever the case is, you find out that you're driving the car in a way. So it is, the relationship here is not a curved, is a curved relationship. So to say this is a curved relationship, it's not linear, it's a curved relationship. Not a straight line. It's not a straight line. And so the question is, how do you now, what do you do to understand these different curves that happen in this, how does the model now sort of make sense of it, right? And mind you, you would realize this during exploratory data analysis. So that's why it's important to understand data analysis. We have done the data analysis part in our where we look at the different ways to explore data and all, and the basic forms of it. I'll be sharing projects as we go to test some of those things. Yeah, so this is the situation we have. So one of the things we want to do is to introduce something which is a polynomial feature. The polynomial feature has become so important that sklearn builds a class of its own for it and say, look, we're going to be using this. So what we can do is to, just show how this is a thing. So I would like a situation where I will build a simple straight line just to show you what it means. And then now show how we can, we build it, we use, what's the word? We generate like a non-linear data, and then we try to fit a straight line into a non-linear data just for you to see what it's like. So to do that, we're going to talk about that. So this is going to be called fitting a straight line to a curved data. This is what this is, fitting a straight line to a curved data. Now we're going to generate the data because, it's the first thing you would do is to generate the data, then we'll see what it looks like. And now go on to fit the data into a model, then visualize it. Right, then when we visualize it and you see, oh, this is what we're talking about. And that's why I had to explain the real life implications of it, because it's ideal to understand the real life implications, so we don't get mad in this idea that we're just doing step by step type stuff. No, it's reality they're trying to fashion. We're trying to fashion all our statistical ideas to reality, and then take abstract real world happenings into statistical concepts, so we can just have that relationship for understanding the way the world works. So the first I'll do is I'll import a few things, which is a normal C. So we'll import numpy as np. Then we'll import matplotlib, pyplots, as PLT. Now, if it's your first time, this is for numerical computing. Typically, we already have a course on this, so you can always check it out. That's data analysis with NumPy, and this is for data visualization. We already also have a course on that. You have access to it if you're signed up to the Data Mentors program. So you can, the Data Science Mentors program, so you can check it out too. And then we would introduce the model class for the scikit-learn model class for building a linear regression model. So to do that, we say from sklearn dot linear model, then we'll import linear regression. So we now have all this stored in our namespace, so we can make use of it or make use of them. Now I'm going to generate a nonlinear data. So this is so I'll generate a non-linear data. Also, while we do this, it's important to understand that every code written is an abstraction of something in reality. And every code written is an opportunity for you to learn Python and understand how Python is used to do a lot of make a lot of abstractions, right? So first off, I'll mp dot random dot seed. So we'll create like a random state instance, so which means if you use the same random state, you can reproduce what we have done. Then we'll create X. Now, if it's your first time, you'll see that I make use of X and Y's. X are features, Y's are the targets, right? And then as you proceed and learn, you'll realize that we have to build our data to represent our scikit-learn model class, which is one, a feature matrix and a target vector, which is basically saying our features and what we're trying to predict. So I'm going to create this. I'm going to say mp.linspace. We use mp.linspace to create like a linear distribution of features, right? So we start from -3 to 3, and then we have like 100 features here. Then we have to reshape the data so that it mirrors numbers of samples and numbers of features. So I'll use the reshape method. Now the reshape method of function is from NumPy, and I would encourage you to take NumPy seriously, because by the time you start deep learning, by the time you've ventured into machine learning and then getting into deep learning, you realize that using tensors in deep learning is typically like the elder brother of the numerical Python family. And so learning numerical Python is a powerful foundation. By the way, numerical Python is like the foundation of data science itself. So it's super important that you understand that, right? Then we'll go on to Y. And then what we're going to do is we're now going to sort of create like a non-linear situation, right? So I say 4 plus, so we're just going to create some noise and then use some quadratic equation to sort of like create some non-linearity. So we're going to say 4 plus x, which is what we have here. Then we square it by 2, we subtract it, multiply it by 2 times x. Then we'll add np.random.rand n, some random features here, 100, starting by 1. Then we flatten it. Now, why are we flattening this? We flatten this because the target feature is just, it's just n samples. So they don't have features, it's just a target vector. So we run this here. So in essence, if I use x dot shape, it tells me that it's 100 to 1. If I use y dot shape, it just tells me it's just no, hold on. This isn't supposed to be. Let me see. So it's 100 by 100, but let me see. Okay, just hold on. So let me try and fit it into this model and visualize. And then if there is if we have an issue with that, then we can always come back. So the second part of what we're doing is to try fitting a straight line. So this is try fitting a straight line. So this is this. So to do that, I would say model, which is going to be our linear. So we're going to instantiate our model, which means all we have here is like a sensible default of a linear regression model. Then we go on to say model dot fit. We're supposed to fit it into x, comma, y. Right. So we've done the fitting in here. So it's looked at our x and y. Then we are now going to say y underscore pred, which is prediction. So we say model dot predict. We're going to take x, is going to give it this. Now, mind you, again, I love to say this every time I do this, that this isn't best practice, because you cannot take the same data that you have fit into the model and use it to predict. It's generally just going to understand what you're doing, but this is for learning, right? So just to put it out there. Then we run this. Now we will try to visualize the result. Now, in the visualizing of this result, that we will show a non-linear relationship. So here, what we're going to do here is we're going to visualize. So we visualize the result. Now, at this point, you think about it to like the kind of problems we see in reality, and when we collect data, we typically want to know what's going on. Again, so that we don't just do this mindless repetition of stuff just because someone else has done it. It typically doesn't help, right? So next, what we're going to do is we're going to use a MATLAB style visualization. Now, if you have watched or you've gone through our introduction to data visualization or the data visualization cohort on the data science mentor program, you would understand that there are two types of visualization principles. There's the MATLAB style, right? There's a MATLAB style, and there is the object-oriented principle where you create objects and you work with them. With the MATLAB style, it's sort of easier to do, but you don't have a lot of control. So it's your V's is going to be inferred. So if you put in some features, it will infer what you're trying to do. But with MATLAB or with the object-oriented style, you can tweak a lot of things. You can choose space. You can choose a lot of things. And so it's ideal to almost always maintain this. Right. So here we'll do PLT dot figure. So we're going to create our figure here. And inside our figure, we want to set our figure size, which is going to be a tuple containing like 8 by 5, like length and breadth or width, right? So this is what we set up. Second, we're going to say plt.scatter. We're going to create a scatter plot. Now, inside the scatter plot, we're going to look at x and y. That's this first part of it is going to be X and Y, which is our data, our inputs, and then our outputs. Then we're going to put the color. We're going to call color here blue. Then the next thing we'll do alpha. Now alpha helps us to create a form of transparency, like visual transparency. So if you put two things together, it can be sort of transparent. Now what we're trying to do is we're going to line up two plots side by side. Right. So that's So we say label. Now with label, we're going to call this the non-linear data. So so this is the main, or let's say this is the actual non-linear data. This is it. So the next we'll do is we are going to plt.plot. So this one we're just going to plot on top of the scatter plot. So that's what's going to happen. And here we're going to have x, which is our x, which is our features, but instead we're going to look at the model we predicted, right? So that's what this one is going to be, y underscore pred. Then we give it a distinct color, and this is going to be red. Then we'll have something called the line width, right? Which equals to sort of like makes it different from what the initial one is, or was. Then here what we have as our label is the linear regression fit. So this is the linear regression fit. So we've done that. Now, as usual, we'll put some titles, plt.title. Now, with plt.title, what we're going to say is we're fitting a straight line through a non-linear data or through a curved data. So here we're fitting a straight line through curved data. Next, we say plt.xLabel, because when we're building our labels, we have the x and y axis. So the x-axis is typically our features. We always mention that. So these are input feature, which is x. Then the y-axis is our target feature. So it's plt.ylabel, which is our target. Our target here is y. Then our plt.legend. So it's just going to automatically check out our legend. In some cases, we might decide how we want our legends to look. We can check a location, but this isn't so, it's not so dramatic, so we don't really need to do that. So we can say plt.grid. We're going to create like grid lines inside. It makes it work. So grid line takes a parameter true. So it's true or false. I think by default it's false. So we make it that. So we say plt.show. At this point, we want to show what we have visualized. And here we go. X and Y must be the same size. X and Y must be the same size. I think you see where I noticed something was wrong here. Okay, C, should we? I knew that this was going to be no, but why must X and Y must be the same size? Okay, let's see which of this. X and Y must be the same size. So where did we get this? Again, we would always have this errors pop up. X and Y. must be the same size. X and Y mustn't be the same size, but they must be this. Okay, so I think I noticed, I think I mentioned at first that we might have this issue here. I think, yeah, let's go back here where we had this. I have the feeling, yeah, why is this 100 by 100? It ought to have been 100. So just out of curiosity, just hold on a bit. Around this, 1, 2. Yeah, so just a bit, I keep thinking I may have gotten something wrong. Yeah, so let me see. Just this one. Let's go here. Yes. Yeah, so that's what it is. So yeah, that was where the error came in. So let's run this again. So something was already there. So this time around it just picks out 1. So now you see what we have here, right? So we're trying to fit a straight line through a curved data. So this is the actual nonlinear data, right? And this is the actual, this is the straight line. And this is linear regression in action, right? So this is linear regression in action. And now in this situation, it doesn't really work well, because if you have to, you have to find a way, right? If you're drawing a curve with a ruler, it won't fit. So that's why we need to transform the data, right? So we don't force this straight line. At this point, right, what we need at this point is, just hold on a bit. What we need at this point is the conversation we've talked about. What the best time for this is for us to now use a linear regression, a polynomial feature fix, or the polynomial basis function. Now, what it does is to understand those all the fixes that come inside of it, and then go on to now fit it in a way that works. Right, so this is the first part of what we're going to be doing. In our next session, we are now going to fix, create a fix, right? When we create a fix, that's the part that makes it work. I'm thinking we should do it in the next session, so we don't overload everything, right? So what we just basically do is to just create a fix. Or we think we should do it right now. No, I don't. I think it would be ideal for us to, yeah. Okay, let's try and let's do a fix. Maybe it would be ideal for us to just see what the difference is. Okay, so what we are talking about is trying to fix this. Now, to use this, we have to use a polynomial feature to fit the curves. So to fit into this curve. And just like we've mentioned, it is a clever trick that says, you know what, we can understand our data, right, by fitting this curve, by making it, trying to fit the curve into it. So I'll just do it really quickly. So here, I'll call this. I was hoping I'll just leave it for another session, but let me just basically say we're going to be using the polynomial features to fit the curve. So that's what we're going to do. So let me, I'll basically just run through this. All right, so the first thing what we want to do is we are going to import the model class, right? So we'll import the model class and we'll import the model class and go on to also create a pipeline so that makes it really fast, right? So from sklearn dot pre-processing, we would import polynomial features. Then we can also say from sklearn dot pipeline, so we would import make a pipeline. I'm going to import make pipeline. So that's the first, these are the model classes we create. Now, what we're going to do here is that we're going to use a 2-degree polynomial feature, which is, remember when we came back here at the beginning, we're just trying to to transform this input, we just look for versions of like x2. Now, like x2 or x3, depending on what we think. If we think it's like the fuel situation where we're trying to know miles per gallon that's burned, we're trying to think maybe there's a way itself makes these changes. And so we figured that by introducing some kind of a tweak to this model, and this tweak is meant to introduce that non-linearity. And then we're trying to see if the model can now make sense of the data it has. So here, what we're going to do is we're going to use a 2-degree polynomial. That's what it's called, a 2-degree polynomial. This. So just use this over here. We use a 2-degree polynomial. Right. So to make this work, we say poly, we call this poly underscore model. And we're going to use the make pipeline. Now, using make pipeline makes it a lot of, pretty efficient. It makes it efficient. So inside it, we're going to say, these are the things we want. We want a polynomial, our polynomial feature, and we want to say the degree to which we tweak it is going to be by 2. And inside our pipeline, we also want to maintain our linear regression inside, instead of calling it differently. So we can now say linear regression. So which is, we fit it in here. Now with this, we just use the poly model dot fit. So we can say x, comma, y. Then we can now say y underscore poly underscore predicts. Right in here, we now say poly model dot predict. Again, I'm going to say it. This isn't best practice. This is just for teaching, right? Just so you can see what we're talking about, because we have to split our data. We have to create split our data so as and then sort of create something where we use different parts of our data to train. It has a very cute name. It's called cross validation. So and we've talked about that earlier on. So you can check out the resources you'll see on cross validation. We did 2-fold and 5-fold cross validation, right? And so we have this, we've done this. Now, what we need to do is now to visualize it. So at this point, I'm not going to write all the very many codes. I'm just going to copy and paste the code. So here I'm going to visualize the improved curve fit. That's what I'm going to do. Visualize the improved curve fit. Right, so let me just get this. It's basically the same thing we've done, but this time around, just a bit. Right, so this is what we have here. So now, just like we had before, we have our XY, which blue, alpha, actual nonlinear. Here we now have XY, but the polypred is now green with a line width through. The label is polynomial fit with a degree of 2. And then we go on to do this. Now you can see what we have here. Now, by fitting it by 2, you sort of come back here and you can see that the straight line, the whole straight line idea didn't really, it does not generalize. It does not generalize based on the intricate linear and non-linear status of our predicted and observed features, or predicted and observed features and targets. And so here now we have worked on this, and you can see that it comes through because of this polynomial fit, the clever trick of trying to tweak your features, the clever trick of trying to tweak your features in order to put into perspective the non-linear status of the training and unseen features. And then this is what you have. So if I have to go back to the beginning where I talked about the car speed versus fuel efficiency, at this point we are recognizing different drivers, the different ways they drive, be it fast, versus slow, or it could be fast and slow, and all that. So this is what the polynomial basis function does. And remember, this isn't a mindless repetition. This is a realization that we're trying to solve a real world problem and taking cognizance of the dramatic way things happen in reality. Right, so that is that for the polynomial basis function. Please, if you have a question, feel free to ask at this point. If it's something you want to watch again, and then you can also drop the question in our Telegram channel, and we can walk through that. All right, guys, so this